So that's an excellent test for independent proofs also. In this case, we already knew this. If you multiply together the two marginal probabilities, you get 34%. Well, we already calculated the joint probability to be 36%. So the events that Markley is profitable and Collins is profitable are not independent. Which leads us to the final application of today. And that in turn usually leads to significant saturation. So Bayes' theorem is a very strange animal because it actually led to a philosophical debate. The idea behind Bayes' theorem is that you start out with prior probabilities of something. The example we're going to look at says you have a prior probability, a belief, that there's only a 40% probability that there's oil in the ground in the sector you own. All right? Now, remember the coin flipping example. What is the probability that there's oil in the ground?
1 or 0. 50?
Well, it's the ground. We're not doing anything with the ground. It's just there, right? So yeah, 1 or 0. Yes?
It's either there or it's not.
It's either there or it's not. Now, the idea though is if you come up with a strategy to behave as if you believe your probabilities, and you have a lot of projects, that actually turns out to be an optimal strategy. But it's still a trick. It's something we use. It's a tool. So we have prior probabilities. The thinking here is that we buy new information. Or we conduct our own study and try to figure it out. You know, punch in some test drills, a few extra wells. That gives you information. Now, you apply Bayes' theorem, and that allows us to get new estimates of the probability of finding oil in the ground. The logic here, I think, is pretty good. Actually, it's not just good; it's unimpeachable, because we've got new information, and that changes our opinion, which is kind of the whole point of human reasoning, right? But even if we did put in a few test drills and found some oil, it could still be the case that those were just by chance, tiny pockets of oil, and there still isn't any that you could really extract. Yes? So in reality, you're not getting certain information. But we're going to look at both of those. We're going to look at the certain information effect and the imperfect information effect. The philosophical problem is that statistics is split up into two, Bayesians and traditional statisticians. And Bayesians appear to actually believe that prior probabilities have some objective value. That there really is something, some probability of there being oil in the ground. And, it's hard for me really to make their case for them since I don't believe them at all, don't believe that position at all. But there really is sort of a very strong split in statistics, and that's continued on into decision analysis and decision sciences and everywhere where you have two different philosophies of decision making. Essentially, the traditional statistical approach for encapsulating the exact same tool, nobody has a problem using the tool, is that you have a bunch of prior information, samples if you will, and sure, it's fine if you use those samples and crunch those into shorthand as prior probabilities. But that's just shorthand. What you really have is all the information. Now you get more information. Well, what you do is you basically take all that information at once and calculate, what your best guess is what's going on now, right? That's the traditionalist approach. One way to approach that, though, to do the same thing, is to apply Bayes' theorem. Now it sounds like a storm in a teacup, but it really causes more trouble than you might believe. Okay, so let's apply this thing. Actually, first, let me just show you how it's derived. So this is the example, and I'm not going to do this until I have the board free. But the idea here is that your belief is that there's a 60% probability the oil field is dry, and it's going to cost you $30 billion to develop it If it's dry, of course, you're not gonna get any revenue out of it. If it's a gusher, you'll get $130 billion worth of oil out of it. So yes, it's a simplistic example, but it retains the structure we need. So we need to figure out what the value of the project is if you can get perfect information. And we also need to know what the value of that perfect information is. In addition, we can look at a consulting report and figure out what the value of the field is if you have access to the consulting report, and what it would be worthwhile for you to pay, the maximum amount you'd be willing to pay. Now, this is the information you're given. So you'll notice it's in the form of a conditional probability, and here's what it's saying. The probability that you're going to get a report that says it's dry, given that the field is actually dry, is 70%. So in English, what would we call this?
Accuracy?
Accuracy, good. And is it possible to estimate this based on past performance for the consulting firm?
Yeah.
Yeah, you look at the previous projects the consulting firm has done, just look at the dry fields and you count the number of times they got it right, yes? And you calculate that for proportion. 70% of the time they got it right. The important point here is you can come up with that number looking backwards. It exists now. Similarly, you can take the fields that turned out to be gushers and count the number of times they correctly identify them to be gushers and calculate that they're right 90% of the time. That too is accuracy, but you'll note it's a different kind of accuracy, right?